All right, so we had gone over the formulas that were on this sheet here. This was a summary of all the formulas that were in 7.5, 7.6, and 7.7. And in the past couple of videos, I was kind of showing you where these formulas came from. And now I want to focus on some calculations using the formulas. All right, so 7.5 is all about the sum and difference formulas. That's these three formulas here. And of course, these are not formulas that you need to have memorized or anything. They're ones that you can just very easily look up in a book. Okay, but let's go ahead and take a look at some examples. There's a couple of problems where they want you to find exact values. And so let's look at some of that now. Suppose that we wanted to find the exact value of sine of 75 degrees. Well, if we were to go to the calculator and type that in, then we'd get some decimal, and of course that would be not an exact, it'd be an infinite decimal. Okay. Now, 75 degrees is not one of my common angles. Okay, that's not, a 30, 60, 90, 45, or, some multiple of any one of those. So the idea here is to use the sum and difference formulas and identify alpha and beta, but do that in such a way so that alpha and beta are common angles that we've worked with. Okay, so if we were to take 45 degrees plus 30 degrees, we would get 75 degrees. Now, 30 degrees and 45 degrees, like we've done lots of things with those are common angles, right? And so I can use my 30, 60, 90 right triangle or my 45, 45, 90 right triangle. And so, okay, well, sine of 75 degrees, that's the same as sine of 45 degrees plus 30 degrees. Alpha is 45 degrees, beta is 30 degrees, and using this formula here, of course I'm adding, so it's going to be sine of 45 degrees times cosine of 30 degrees plus, since I've got a plus there, cosine of 45 degrees times sine of 30 degrees. And like I said, I'm now using my common triangles. So sine of 45 degrees, opposite of our hypotenuse, the opposite side would be 1, the hypotenuse would be root 2. Cosine of 30 degrees, adjacent over hypotenuse, the adjacent side would be root 3, the hypotenuse would be 2, plus cosine of 45 degrees, the adjacent side would be 1, the hypotenuse would be root 2, and then sine of 30 degrees, the opposite side would be 1, the hypotenuse would be 2. Simplify that. Okay, and I'm also rationalizing the denominator. Your book is rationalizing the denominator on a lot of these problems, unnecessarily in my opinion, but that's still how they're giving the answers. So now we've got our common denominator of 4, and I can add the numerators root 6 plus root 2 all over 4, or here'd be the exact number in simplified form. And of course, simplify is, as far as you can go there. Here's another one. Suppose that we want to compute sine of pi over 12. Well, pi over 12, again, is not one of my common angles. So I want to think of some common angles such that when I add or subtract, I get pi over 12. Pi over 12 is the same as 15 degrees in degree mode. So if I were to take 45 degrees minus 30 degrees, I'd get 15 degrees. Now I'm using radian measure, so 45 degrees in radians would be pi over 12. 30 degrees in radians would be pi over 6. Pi over 4 minus pi over 6 is pi over 12, and now I can refer to my sum and difference formula. Okay, I'm subtracting the angles here. Alpha is pi over 4, beta is pi over 6. So I want sine of pi over 4 times cosine pi over 6 minus cosine pi over 4 times sine pi over 6. And that allows me to then use my triangles. So sine of 45 degrees, that was 1 over root 2. Cosine of 30 degrees, that was root 3 over 2, minus cosine of 45 degrees, that's 1 over root 2, and then sine of 30 degrees, that's 1/2. So we're going to have something very similar to what we had there in the other problem, only we're subtracting inside the parentheses. Okay, tangent of 195 degrees. 195 degrees is not a common angle, so I want to think of some common angles that add or subtract to get me 195 degrees. Well, if I had 150 degrees plus 45 degrees, that would give me 195 degrees. And a 150 degree angle would produce a 30, 60, 90 right triangle in quadrant 2. Of course, we already know that 45 degrees is a common angle, right? So now I'm using the sum and difference formula here for tangent of alpha plus beta. Alpha is 150 degrees, beta would be 45 degrees. So that would give me tangent of 150 degrees and then plus, since I'm adding, tangent of 45 degrees divided by 1 minus, since I'm adding there, tangent of 150 degrees times tangent of 45 degrees. Tangent of 150 degrees, again, we'd be working with a 30, 60, 90 right triangle. It would be a 30 degree angle in quadrant 2. So opposite over adjacent, opposite side would be 1, adjacent side would be negative or root 3. And then plus tangent of 45 degrees, 1 over 1 is 1. Divided by 1 minus tangent of 150 degrees, we just said that's 1 over negative root 3, and then tangent of 45 degrees is 1. Okay, and then I'm simplifying. I'm also getting a common denominator there, and also rationalizing the denominator. In complete simplified form, you would get 2 minus root 3 as the exact solution then. Okay, and here's another one. Cosine of 40 degrees times cosine of 10 degrees plus sine of 40 degrees times sine of 10 degrees. Well, I don't know what any one of those are, right? Because 10 degrees and 40 degrees are not common angles that we work with. So if we were to use the sum and difference formula, the second one, cosine alpha, cosine beta plus sine alpha, sine beta, that is the same as cosine alpha minus beta. Okay, so I'm still using the sum and difference formula, just reading it right to left. Alpha would be 40 degrees, beta would be 10 degrees, and so that would give me cosine of 30 degrees, which, okay, the adjacent side would be root 3 and the hypotenuse would be 2. Root 3 over 2 then would be the exact value of that. Okay, here's another example. Find the exact value if cosine alpha equals 1 over root 5 and alpha is an angle in quadrant 1, is what they're telling us there. And sine beta is equal to negative 4/5 if beta is an angle in quadrant 4, is what they're telling me here. All right, well, I want to draw my triangles representing the situations here. Alpha and beta are not going to be common angles since these are not, numbers that would be formed from 30, 60, 90 or 45, 45, 90 right triangles. That's okay, I can still build my triangle here. So cosine of an angle is adjacent over hypotenuse. The opposite side, I'll just temporarily call that x. This angle is alpha. Use the Pythagorean theorem. X squared plus 1 squared would be equal to root 5 squared. Subtract 1, x squared is equal to 4. Take the square root of both sides, and x would be plus or minus 2. The hypotenuse, so you're going above the horizontal axis there, x would be 2. And then over here, I've got the angle beta set up. Sine of beta is negative 4/5. Sine of an angle is also opposite over hypotenuse. The opposite side is negative 4. The hypotenuse is 5. The adjacent side, I'll just call that y temporarily. And use the Pythagorean theorem. Y squared plus negative 4 squared is equal to 5 squared. If you solve for y would be plus or minus 3, but we're going to want 3, right, since we're going to the right of the center there. Of course, pay attention to whether the number should be a positive or a negative. That's a mistake I'll see students make, because it should have been a negative when they wrote a positive or something like that. And all right, so now that I've got these triangles, like these are the, when I say find the exact value, I'm talking about these values here, these calculations that we're going to be doing. So let's find the exact value of sine of alpha plus beta. Well, I've got my individual triangles drawn for these individual angles, and so using the sum and difference formula for sine of alpha plus beta, I've got that written down there, and I can then refer to these triangles. So sine of alpha is opposite over hypotenuse is to be 2 over root 5. Cosine beta, okay, adjacent over hypotenuse, that'd be 3/5 plus cosine alpha, well, that was given to me, that's 1 over root 5, times sine beta. That sine beta was also given to me, that's negative 4/5. 6 over 5 root 5 minus 4 over 5 root 5 would be 2 over 5 root 5, which would be the exact answer there. Okay. And part B, I want to find cosine of alpha plus beta. So I want to use my sum and difference formula here for cosine alpha plus beta. And I've got that written down. Okay, and I can now get the individual numbers. So cosine alpha is given to me. That was 1 over root 5. Cosine beta, we've already found from earlier, that was 3/5. Minus sine alpha, so from earlier we said that was 2 over root 5 times sine beta. Sine beta was given to me, that was negative 4/5. 3 over 5 root 5 minus a negative would be plus 8 over 5 root 5 would be 11 over 5 root 5 then. Okay, part C, tangent of alpha minus beta. So I'm using my identity here, this one, and that way I can, get the individual angles and not the sum or difference of them. Okay, now I can compute tangent alpha. Here's alpha, opposite over adjacent. That'd be 2 over 1 is 2, minus tangent beta. Okay, again, opposite over adjacent, so that'd be negative 4 over 3, negative 4/3, divided by 1 plus tan alpha is 2 times tan beta is negative 4/3. Simplify that, 10/3 divided by negative 5/3, flip the denominator and the 3's cancel. 10 over negative 5 is negative 2, would be the exact answer then. Okay, notice how the triangles drawn ahead of time are key to the calculation. We must have those, of course. There's a couple of identities mixed in where you're establishing the identity. We were doing a lot of that in section 7.4, okay? And so now that we've talked about more with identities, we can do, we can build many more identities, since we were just kind of restricted to the basic identities that I said, these are ones that you'd want to have memorized. Okay, so let's establish this identity here. Cosine alpha minus beta divided by sine alpha cosine beta is the same as cotangent alpha plus tangent beta. Well, let's get everything in terms of a single angle, not an alpha minus beta angle. So cosine alpha minus beta, using that sum and difference formula, is cosine alpha cosine beta plus sine alpha sine beta. And so I've got that written in the numerator. I've kept the denominator as is. And now I'm going to split this single fraction into 2. That's going to allow me to then cancel the cosine beta terms and then the sine alpha terms. Cosine alpha divided by sine alpha, it would be cotangent alpha. And then after I cancel these, sine beta over cosine beta would be tangent beta. Okay, and that's where I had to get to on the right side there. Remember that when we establish an identity, you're starting with one side and you're algebraically manipulating that to get to the other side, and along the way you'll want to use some other known identities. Okay. Here's one more example. Find the exact value of sine of cosine inverse of 1/2 plus sine inverse of 3/5. Okay, I'm going to let alpha be cosine inverse of 1/2, that's just an angle, and then beta be sine inverse of 3/5, again that's an angle. So really in this problem I'll need to compute sine of alpha plus beta. Alright, so later on I'll be using my sum and difference formula. Now if alpha is cosine inverse of 1/2, that would mean that cosine alpha is 1 over root 2 for when alpha is between 0 and pi. Remember the conditions on the cosine inverse curve are that the range is 0 to pi. Okay, and of course I'd want to know that, right, because I'm going to be drawing my triangle. It's going to be either in quadrant 1 or quadrant 2. I know I'm going to be in quadrant 1 since the adjacent side and the hypotenuse are both positive. The adjacent side is 1, the hypotenuse is 2. The leftover opposite side then would be root 3. And, all right, so then over here, of course that's a 60-degree angle. If beta is sine inverse of 3/5, then sine beta would be 3/5. The conditions on the range of the sine inverse curve is that the angle has to be between negative pi over 2 and pi over 2. So I know I'm going to be in quadrant 1 or quadrant 4. Well, I'm going to be in quadrant 1 since the opposite and the hypotenuse are both positive numbers here. Opposite side is 3, hypotenuse is 5, the adjacent side would be 4. 3 squared plus 4 squared would give me 5 squared using the Pythagorean theorem. Now, I'm ready to compute sine of cosine inverse of 1/2 plus sine inverse of 3/5. So that's the same as sine of alpha plus beta, like I said. We'll be using our sum and difference formula here, the very first one on the sheet. And so I've got that written here. Sine of alpha, well, here's my angle alpha, opposite over hypotenuse, that'd be root 3 over 2, times cosine beta, here's angle beta, adjacent over hypotenuse, that'd be 4/5, plus cosine alpha, well, cosine alpha is 1/2 from earlier, and then times sine beta is 3/5, again from earlier. So, okay, 4 root 3 over 10 plus 3 over 10 would be 4 root 3 plus 3 all over 10 if you were to write that in a single fraction form. Okay, and that number would be the exact value of this guy here. All right, that's all I had in section 7.5. So be sure to look at the homework problems that are on page 499.